Okay, so this is part 2 for the screencast on magnetism, chapter 18. We've already talked about the magnetic force and the magnetic force on wires. Now the question is going to be, what creates the magnetic field? So the magnetic field is always denoted by B. It's a vector. It's a function of position. And what creates it? All right, so here's a little introduction. We've already defined B in part 1 of the screencast. We said that a charge, an electric charge, Q, moving with velocity V at the position X, experiences a force Q V cross B of X. Or the force on a wire carrying a current I in a magnetic field. It's the sum, so this symbol means sum. It's really a symbol from calculus, but we don't use calculus in physics 232. It's the sum of all the forces on little parts of the wire. So if you have a wire carrying a current I in a magnetic field, which is, say, pointing away from you, the force is in the direction of the current cross the field. So that means the force will be in this direction. And it comes from all parts of the wire. Each little section of the wire experiences a force. And the force on a little section of the wire is the current I times the length cross the magnetic field. And to get the complete force, you have to sum all the parts of the wire. Electric currents create magnetism. This is section 5 in chapter 18. Let's consider forces between magnetic dipoles. Suppose I have a magnetic dipole. A magnetic dipole is an electric current loop. So I have current flowing around a loop. And now, the definition of the dipole moment. Dipole moment, we usually call it M, sometimes mu. The dipole moment of a current loop is the current times the area, pi r squared for a circular loop, times the unit vector perpendicular to the loop. So this is a planar loop. Let's say this is the z direction. So this is a planar loop in the xy plane. It has a dipole moment M equals IA k hat. Well, that creates a magnetic field, a dipole field. by the right-hand rule, the magnetic field is in the direction of M at the center of the loop. So there's a magnetic field created by the dipole where, let's say, red is the North Pole. The magnetic field comes out of the North Pole. So this side of the loop is like a North Pole, and this side of the loop is like a South Pole. So there's a dipole field. Let's put it in a different color. So there's a magnetic field. It comes out of the North Pole, goes into the South Pole, and circulates around. And similarly down here. So a dipole is a source of magnetism. It creates a magnetic field. By the right-hand rule, if your fingers curl in the direction of the current, then your thumb points in the direction of the dipole moment. So for currents in opposite directions, the dipoles point in opposite directions. You have a North Pole near a North Pole, that will give you repulsive force. On the other hand, if you have two dipoles with currents in the same direction, then the North Pole of this dipole on the left will be closer to the South Pole of this dipole on the right, and that will give you an attractive force. So there are forces between magnetic dipoles, and magnetic dipoles are not combinations of monopoles. There are no isolated monopoles. Magnetic dipoles are created by current. So, for example, we could draw this picture for magnetized iron. Each iron atom has an electron current. There's an electron current flowing around the atom, each atom. And if all of those dipoles are pointing in the same direction, then you'll end up with a North Pole on one side and a South Pole on the other side, because the magnetic field always comes out of the North Pole and comes back into the South Pole. Now, there are two relations between electric current and magnetism, or magnetic field. Electric currents create magnetic fields, and that's what we're talking about in today's screencast. And the other part of the interaction, when a charged particle moves in a magnetic field, it experiences a force, Q V cross B. That's the Lorentz force. And we talked about that in the first part of the screencast. Or if you want to consider a current in a wire, the small amount of force on a small length of wire is I times the length across the magnetic field. All right, so what we're interested in now is this part. How an electric current creates a magnetic field. Now, of course, most people, if you ask them, where does a magnetic field come from? They'll say, well, it comes from a magnet. They won't say it comes from an electric current, but it does come from an electric current. It comes from electric currents in the iron atoms in the iron. So before we go on to the relation between B and I, let's go over a brief history of the science of magnetism to see where this fact came from. Because this is something which is not exactly obvious. It's not obvious at all. I mean, magnetism was known long before the connection to electric current was known. I mean, magnetism has a very ancient history. So let's go over a little bit a brief history of the science of magnetism. The first question is, who discovered magnetism? And we know the answer to that. It was a man named Thales. Thales of Miletus. Miletus was the name of the town where he lived. He lived 624 to 528 BC. So when he was alive, Miletus was part of the ancient Greek Empire. He is considered the first scientist in Western civilization. And even among philosophers, he's considered the first philosopher in Western civilization. You know, the civilization of ancient Greece was famous for its philosophers. And Thales was considered the first one. He was not only a philosopher, a scientist, also a mathematician, also an investor. He made a small fortune by investing in olives. Anyway, Thales of Miletus was the first person to discover magnetism. How? Well, he observed that certain iron ores exert forces on iron objects. Those iron ores are called lodestones. The iron ore is called magnetite, and the rocks are called lodestones. And a lodestone exerted a force on iron objects, and Thales described that force. Now, who named the phenomenon magnetism? Well, that was named by the English scientist William Gilbert, who lived at the time of Queen Elizabeth, not the current Queen Elizabeth II, but the first Queen Elizabeth, the time of William Shakespeare. Well, William Gilbert named this phenomenon magnetism after Magnesia, which was the province in western Anatolia, where Thales lived. The city of Miletus was located in a province called Magnesia, and Magnesia is where they found lodestones, magnetized rocks. Well, now moving into more the modern era, Hans Christian Ørsted was a Danish scientist, and he observed, kind of by accident, that an electric current deflects a compass needle. In 1820, during a lecture on electricity and magnetism, Hans Christian Ørsted discovered that a wire carrying electric current, so that's this current I, exerts a torque on a magnetized compass needle. He was showing demonstrations of electrical currents, and there was a compass needle nearby, and he noticed that when the current was flowing, the compass needle wasn't pointing north. It was pointing in the direction around the wire. And so that's how it was discovered that electric current has a magnetic effect. Today we would say it creates a magnetic field. And if the magnetic field is strong enough, which is to say if the current is large enough, it will exceed the magnetic field of the Earth, and the compass needle will respond more strongly to the magnetic field created by the wire than it does to the magnetic field created by the Earth. Now, the same year, two French scientists, Biot and Savart, wrote down this equation for the amount of magnetism, say dB, created by a small amount of current. So let's say a current I in a length of wire ds. So a small wire with length ds carrying current I, that little portion of the wire will create a magnetic field dB, which is mu naught I ds cross r hat over r squared. So mu naught here is a universal constant, which depends on the system of units. So mu naught is just a constant of nature. It's called the permeability. It's really called the permeability of empty space, or the permeability of vacuum. The picture looks like this. If there's a current in this way, I, in a small length of wire, delta S, and you come out to some point here, so let's say this is a point X where you're observing the magnetic field. There'll be a magnetic field. Now, what direction will it be? Well, let's show the magnetic field in a different color. At this point, the magnetic field will be pointing out towards you. You have to view this in 3 dimensions. At this point, it's pointing out towards you. Down here at this point, it'll be pointing away from you. So I'll indicate the 3rd dimension pointing away from you as an X, the 3rd dimension pointing towards you as an I, as a point. And the magnetic field curls around the current. So that's the magnetic field. Now, by the right-hand rule, ds cross r will be outward at this point. It'll be inward at this point. And the strength of the magnetic field decreases as 1 over r squared. So as you move farther away from the wire, r is the distance to this. So r is the distance to this little length of wire, this little bit of current. As you move farther away from the wire, the magnetic field decreases as 1 over r squared. It's an inverse square law. The same year, 1820 again, Jean-Marie Ampère, another French scientist, more of a mathematician really than an experimental scientist, Ampère showed that there's this relationship between magnetic field and electric current. The line integral, or the sum of the magnetic field dot ds around a loop, so B dot ds around a loop, let me show that over here. Let's use a different color. So here's a little loop in space. And again, you have to view this in 3 dimensions. So here's a little loop. We call that C. It's a closed curve. And there's current going through this loop. So let's put the current in, I don't know, let's put the current in red. So there's current going through this loop. There could be wires going through the loop. And B here points in the direction tangent to the curve. Well, if I add up around the loop, B times the length, it's mu naught, that same constant, times the current through the loop. So this is I through the loop. It's geometrically complicated. You have to view it in 3 dimensions. You have a magnetic field curling around the electric current. All right. Faraday, around the same time, explained how to create a motor. You could create a motor from a current in a loop. Now, that's not the production of magnetism by current. That's an example of magnetic force. But anyway, it was sort of coincidental with all these studies of electricity. A bit later, Faraday showed how you can create generators to generate electricity. And that's called electromagnetic induction, and we'll study that next week. Then finally, Maxwell, the great Scottish theoretical physicist, derived the field theory for electricity and magnetism. And it also applies to optics, because light is an electromagnetic wave. And Maxwell expressed it this way: the curl of B is mu naught, that universal constant, times the current density. Now that was quite a few years later, but anyway, this is sort of the history of the science of magnetism. And Maxwell's field theory, we still use it today to understand magnetism and electrical engineering. All of electrical engineering is based on Maxwell's field theory. Here's the principle of the electric motor. You have a magnetic field, and you have a coil of wire which can rotate around an axle. Well, the direction of the force on this side of the wire, this side of the loop, will be I cross B. So I points into the page, B points to the right, so I cross B will be this direction. So there'll be a force on this side of the current loop. On the other hand, over on this side, I points out of the page. So I cross B points upward. So you see there is a force all the way around the loop, and the sum of all the forces around the loop would be zero. So a current carrying loop in a magnetic field does not experience a net force, but it experiences a torque, because this force is at a distance, some distance r from the axle, and this force is also at the same distance r from the axle, so there's a torque. And as you know from mechanics, torque produces angular acceleration. So this loop will accelerate around the axle. It'll rotate around the axle until the speed is high enough that the frictional force balances the magnetic force. But the magnetic force is what produces the rotation of a rotor inside an electric motor. It all comes from the force is I dl cross B. This equation is wrong. The force on a piece of the wire is I times the length of that piece cross B. Now, if you take apart the starter motor in a car, it'll look something like this. It'll be very complicated. It's more than just a coil of wire in a magnetic field. For one thing, the magnetic field will be created by an electromagnet. That's an example where current creates a magnetic field. So you have something called field windings. You have a commutator to reverse the direction of the current. And I guess these are the wires that experience the force, the torque. So this is the loop. It's actually many loops of wire. These are magnets. Now, they don't have to be permanent magnets. They can be electromagnets. So this is the source of the magnetic field. You know, this part is the switch. It's a solenoid. It's a switch. This is a starter motor, so it runs when you turn the key. When you turn the key, that provides current to the solenoid. That pulls in the this plunger, that produces the current in the field windings. I guess the field windings, let me think. The field windings must create the field, I suppose. So that creates the magnetic field. So this is not the source of the magnetic field. It's the field windings. It's an electromagnetic. It's an electromagnet. But there are currents in these windings. No, I said that wrong. These are the field windings. So this is the source of the magnetic field. Yeah, these are the field windings. So current from battery goes through the field windings, creates a magnetic field. These are the windings with the current. I also get that current from the battery as well. But that's the current that experiences the torque. So that's the current that experiences the magnetic force. But the point is, it's electric currents in the field windings that create a magnetic field. That's the subject of today's screencast. Well, the simplest electric current is just motion of a single charge. So if an electric current, which is a motion of many charges, creates a magnetic field, then the motion of one charge would also create a magnetic field. So what's the magnetic field created by a single moving charge? You have an electric charge with charge Q, moving with a velocity v. What's the magnetic field? Well, it's given by this equation, which is related to the Biot-Savart law. The magnetic field at a point x, that's not the position of the charge. The charge is at the origin. So the charge, in this picture, the charge is here. Here's the charge. And I'm considering the magnetic field here. So this is some random point in the volume. And this is the charge Q, located at, well, the center of this coordinate system. The magnetic field at point X is mu naught over 4 pi, QV cross R hat over R squared, where mu naught is that permeability of vacuum, Q is the charge of the moving particle, V is the velocity of the moving particle. R is the vector from, let's put that in a different color. R is the vector from the particle to the point where I'm measuring the magnetic field. So this is R. It's the position where I'm measuring the field relative to the position of the particle. So it's the vector x minus xq. That's R, and R without an arrow over it is just the length of that vector. So that's just the distance from the charge to the point where I'm determining the field. And because of the cross product, the magnetic field directions kind of circulate around the position of the axis of the velocity. So I guess I should have said, this is the velocity. Particle is moving in this direction. The magnetic field is circulating around that direction. So to speak, there's a current in this direction. I call that the z-axis. There's a current in the z direction. It's a very trivial current. It's just a single charge moving along the z-axis. At this particular instant, it's located at the origin. And the magnetic field circulates around that. The strength of the magnetic field decreases as 1 over the distance squared, distance to the charge. If we used cylindrical coordinates, rho, phi, z, we use the z-axis. So let's say x is just the position of this point, is rho times rho hat plus z times k hat. And v is v0 k hat, so that's a velocity directed in the k direction, in the z direction. So this is the z direction. That's the direction of k hat. The magnetic field is in the phi direction. The phi direction is this way. It's an angular measure around the axis. So b phi times phi hat will be the magnetic field vector. It'll depend on the coordinates, rho, phi, and z. These are the cylindrical coordinates. It'll be mu naught q over 4 pi. So here's the mu naught q over 4 pi. The velocity will be v times k hat. Then you'll have k hat cross r hat. So you'll have v0, k hat cross r hat over r squared. That'll just be phi hat over rho squared plus z squared. Rho squared plus z squared is r squared by the Pythagorean theorem. So these are these coordinates. Z is along the z-axis. Rho is perpendicular to z, and phi is the angle going around the z-axis. Now, I don't know if you'll have to use cylindrical coordinates in any of the long kappa problems, but you could. Well, that was the magnetic field created by a single moving charge. If you have many charges, instead of Q times V, which was the factor producing the magnetic field for a single moving charge, you would replace that by current, call that I, times length, the length of a little section of a little segment of wire. V, of course, is a vector. The section of the wire is in the direction of the wire. So Q is coulombs, V is meters per second. So this is coulombs times meters divided by seconds. I is amps, or coulombs per second. This length is meters. So this is coulomb per second times meters. So these are the same, at least in terms of units. This corresponds to a large number of charges making up a current I in a region, in a section of the wire of length ds. So here's the magnetic field created by a little section of wire. It's mu naught over 4 pi, I ds cross r hat over r squared. Or again, r is x minus x prime. Here, x is the point where I'm measuring the magnetic field. X prime is the position of ds, position of the source. So again, this is the vector from the source to the point where I'm measuring the field. And you see this has exactly the same as the moving charge with this replacement. This is what's called the Biot-Savart law. Now, the magnetic field created by current in a long wire, it has more than just one little section of wire, means I have to add up all the magnetic fields. This is yet another example of the superposition principle. If I have many sources, the total magnetic field will just be the sum of the magnetic fields of each source. So I'd have mu naught over 4 pi I ds cross r hat over r squared, and I have to sum over all parts around the where the current is flowing. Now in this case, I sum over all the parts of the wire. So I'm talking about a wire in the z direction. And here's a little section of the wire. So that's ds. And I'm trying to figure out what's the magnetic field at this point. This is the point X. Well, I ds cross r hat over r squared gives me the part, this didn't show up very well, ds. So I ds cross r hat over r squared, this will be the vector r. That is the contribution of the magnetic field from this part. But I have to sum up over the whole wire. In calculus, that's called the integral. And now, in Physics 232, we don't do calculus, but I suppose some of you might have taken calculus. This is a kind of integral calculation. You end up with ds is dz. Distance is rho over rho squared plus z squared to the 3/2 power. And then the direction is phi hat. And you can do that integral using methods of calculus. And you have to integrate over the entire wire. So stretching from z equals minus infinity up to z equals plus infinity. Or just, for a very long wire, you could just approximate it as infinitely long. And this is the answer. So after a little bit of calculus, not very advanced calculus, B at that point X is the magnitude mu 0 I hope you're taking notes because you're going to need this for the homework, over 2 pi rho. You'll need this on the ln kappa. That's the magnitude, and the direction is phi hat. It's the angle around the z-axis, around the current. So the magnetic field circulates around the current. And for a single little section, it's an inverse square law. But if you add up the effects over the whole wire, it becomes not an inverse square law, but just goes like 1 over rho, where rho is this distance. It's the perpendicular distance. It's the cylindrical distance. It's the distance from the point where I'm measuring the field to the axis. So that's called the perpendicular distance to the wire. This is in the book. So you see section 5. They don't have the calculus, but they write down the result and explain it. And this is something you'll need for the homework and for whatever exam questions. All right, so that's a particular case. That's a case of a long wire. There are some other cases in section 5. Finally, we have Ampere's law. Now, again, this really requires calculus, but we'll just sort of understand it without calculus. It's a theorem in mathematics. It says, if you integrate the magnetic field around a closed curve, the result is mu 0, that universal constant, times the amount of current going through any surface bounded by the curve. So we have some closed curve. That's C. Inside that curve, there's a surface. Put that in a different color. So there's a surface here. There are actually an infinite number of surfaces I could draw. It doesn't have to be a flat planar surface. But anyway, any surface bounded by C. So that's the surface. That's S. And there's current going through that surface. So let's say there's a current there's current going through the surface. So you have to view this as a three-dimensional picture. So that's the current. And now there's a magnetic field that curls around the current. So let's put the magnetic field in, I don't know, that current, that color. There's a magnetic field that's curling around this current. Well, the line integral, or the sum of all the little sections of magnetic field around this loop is mu naught times I through the loop. This is a theorem, so we should be able to prove it. Let's prove it by an example. Let's suppose we have a long, straight wire carrying current I. So let's say that this, all right, so here's the, well, let's see if I can draw it a little better. Here's the loop, and here is the wire carrying current I. Well, there's a magnetic field that curls around the wire, so I can add the contribution of the magnetic field around the loop. That'll just be the current going through the wire, according to Ampere's law. Now, we know the magnetic field. You know, the magnetic field, let's put the magnetic field in, I don't know, let's use a different color now. Let's put the magnetic field in black. The magnetic field is around this way. It's curling around the wire. So that's the magnetic field. Well, we figured that out a minute ago. That's mu naught I over 2 pi rho phi hat. So there's the magnetic field. And we wrote that down a minute ago. The magnetic field due to a long wire. And now we have to have the length of the little section around this wire, or I mean around this loop. So a little section of this loop, let's say here, a little section of this loop, ds, will have a length rho times d phi, and it'll be in the direction of phi hat. So phi hat dot phi hat is 1, the rho cancels the rho, integral d phi around a closed loop is 2 pi. Or another way to say it is the circumference is 2 pi rho. The rho will cancel, the rho is the perpendicular distance, that'll cancel the 1 over rho. So I end up with mu naught I over 2 pi times 2 pi. It's just mu naught I. So indeed, that example I had before of the magnetic field due to a long wire agrees with Ampere's law. Now, Ampere's law is important because it can be used to derive and figure out the magnetic field in the case of certain highly symmetric current systems. So there's an example in the book, which is the case of a solenoid. A solenoid is just a helical wire. It's just a helix carrying current. So it's a cylindrical it's a cylindrical current, I guess you could say. It's like a cylinder with a current going around the cylinder. It's a helix. And from this theorem, you can show that the magnetic field inside the solenoid is mu naught N over L, where N is the number of turns of wire and L is the length of the helix, times the current I, in the direction of k hat. That is to say, parallel to the axis of the helix. That's equation 1810. That's something that you can pretty easily show obeys Ampere's law by considering a loop that cuts through the current in the helix. That's a result you're going to need for the long kappa problems and for the exam questions about magnetism. All right, so this completes the screencasts about magnetism. Now you should go on and start doing the long kappa problems for this week.